Hi everyone. So let's do another lecture summary here. Before going to field quantization, let's have a reminder of what quantum mechanics actually means and how it works. And one of the key features of quantum mechanics is that the momenta and positions become now operators, and you can think of them as matrices, and that they can act on a vector. Yeah, the vector is the state that lives in this Hilbert space that we talked about last time. And um, observables in the end of the day in quantum mechanics are expectation values of the operators. An important fact about matrices is that they are the order in which they are applied plays a role. So for a generic matrix, A times B is not equals B times A, only if they are very specific, for example, diagonal matrices. You can switch them, but in general, you can't. So let us define this quantity that we have here. We show that we write it with the square brackets, let's say, and we call it the commutator. And the square brackets of A and B is just A times B minus B times A. So this quantity measures by how much it matters when you switch the order of the two operators. So in quantum mechanics, for a system of n particles, the commutator of position and momentum is 1 if the particles are, or is I if the particles are identical, and is 0 if the particles are different. So if the position and momentum correspond to different particles. Then the positions and the particles of the positions and the momentum of the particles commute to 0. Their commutator vanishes. And I think we talked about it last time that this relation here is the reason why we can't measure momenta and positions with arbitrary precision, because we have the so-called uncertainty principle. It is really connected to the fact that momentum and the position operators do not commute with each other and are affected by each other. Let us go to the most famous example in theoretical physics, the harmonic oscillator. It's basically used for almost everything. And one of the reasons is that it's one of the few systems that we can really solve analytically and write equations for. We had the Lagrangian on the blackboard the last time, but let me just define this quantity, frequency of the oscillation by the ratio of the spring constant and the mass and write it up here. I can do it just with absorbing coefficients, but this is more convenient for working with this system. So after the Legendre transformation, we flip this sign into a plus, and so we have the Hamiltonian operator of the harmonic oscillator. So far, it looks classical, but now we enforce the commutation relation between the momentum and the position to be equal to I. So that is the quantization procedure, actually. So just by doing that, we are already in the quantum world. Now, how can we mathematically now describe and see what actually happened when we enforce this commutation relation? There's a trick, there's a neat trick. We see that the Hamilton operator is actually a sum of squares. It looks like some quantity x squared plus y squared, basically x and y being p times some coefficients. But we know if we go to the complex numbers, we can write x squared plus y squared as x plus I y times x minus I y. Yeah? And let us call this combination A and the other combination A star, or since we're talking about operators, we don't take just the complex conjugated, we take the Hermitian conjugate. So it's called A dagger. Yeah. Because we yeah, also transpose. So if you think about matrices, it's complex conjugation and transposition at the same time. Okay, we see that we can write this A and A dagger as Q plus IP and Q minus IP, where we also have fixed the coefficients. And I will show you in a second why these coefficients had to be this way. But the basic idea comes that we want to decompose the Hamilton operator in these complex numbers by writing it, by seeing that it's a sum of squares. Now we can solve for Q and P. We can solve for Q and P and have the Q and P as a function of A and A dagger is given by that. A sum of the A and A dagger is Q, and the difference with an I up front is the momentum. And now we can check the commutation relation A to, comma A dagger is equal to A dagger minus A dagger A. You can write it out explicitly. Then we check the combinations that are cross terms that contain P and Q, because P and Q and Q have vanishing commutators, right? We write it all out, and we find that is equal to I PQ minus QP. This is just equal to minus I commutator of Q and P, which you remember is I, so it's minus I times I is 1. So the reason why I chose the coefficients here and here to be as they are is to have the A and A dagger to commute to 1. And again, we will see why it is important. So we can then show, plugging the definitions for A and A dagger up here in the Hamiltonian, we can see that it is equal to 1/2 omega A dagger plus A dagger A, or using the commutation relation, flipping the order of A and A dagger gives us 2 times A dagger A. It gets rid of this 1/2. But this 1/2 still multiplies the 1 from the commutator, and we have this 1/2 up front here. This is very interesting. We will come to that in a second, why there is this constant factor in the Hamilton operator. Now we can also check that the commutator of A dagger and A with the Hamiltonian is given by omega with a positive sign and omega with a negative sign. Now we can think about the meaning of A and A dagger. What is the energy eigenstates? Energy eigenstates, for example, if you think of the time-independent Schrödinger equation, we have when the Hamilton operator acts on a state and just gives like a number times the state. The state is called an eigenstate of the Hamiltonian because there is no time explicit time dependence, and the Hamilton operator just brings down a number, which is the energy. Now, just a reminder again, the observables, the physical observables in quantum mechanics are expectation values of operators. For example, energy is expectation value of the Hamilton operator over some states. Now, since if we choose the states to be an energy eigenstate, the action of the Hamilton operator on the state just gives you a constant number E. We can pull it out of this product. The product is also a norm, and we know that the normalization of all wave functions in quantum mechanics is 1, because it essentially is the total probability of finding this particle somewhere, which is always 1. So we see that this is indeed the energy, the expectation value of the Hamilton operator over this state psi. Now, just again a reminder, quantum mechanics operators that have something to do with observables are necessarily Hermitian. That means the Hermitian conjugate operator dagger has to be equal to itself. And this is true because there is a theorem that states that Hermitian operators have only real eigenvalues. And so these expectation values, in fact, are some superpositions of the eigenvalues of the operators. You can also prove that. in some basis choice, and the observables necessarily have to be real, and that induce enforces for all operators that correspond to like physical observables to be Hermitian. Now, what happens when we have the A and A dagger acting on these energy eigenstates? Okay, you can ask the question, what is the energy of A dagger hitting the energy eigenstate with energy E? So we have here H of acting on A dagger psi. We know how H commutes with A dagger, right? H A dagger minus A dagger H equals to omega A dagger. We had it before on the blackboard. So we can bring this to the other side. So H A dagger is nothing else but A dagger H psi plus omega A dagger psi. Now, we know how H acts on psi, just gives a E because it's an energy eigenstate. And we can pull out E and omega because they're constants. So we have E plus omega times A dagger psi. So H acting on this state gives us now the energy E plus omega. That means that the energy of the state has increased by the frequency omega. So the action of this operator A dagger on a state with energy E increases it and takes it to the energy state E plus omega. Same, we can prove that A acting on E, psi E, reduces the energy by a factor omega. So it takes it to a state that is E minus omega. That's why we call those operators the ladder operators, or in other words, creation operator or annihilation operator for A and creation operator for A dagger. Now, an interesting statement is that if the energy is bounded from below, and it should better be, that there should be some lowest energy state, we have to have a ground state that we call the zero in this ket notation. And this we call the vacuum of the ground state of the theory. Well, for now in quantum mechanics, let's just call it the ground state. Because A reduces the energy, the annihilation operator of the states, and the ground state can't be reduced any further, so A just annihilates it and gets rid of the state. So this is a true statement. A hitting the ground state gives zero. So now again, going back to this interesting fact that how the Hamilton operator looked so we can see that when it hits the ground state, that we get omega on 2 times the ground state. So the ground state, in fact, has a non-zero, non-vanishing energy. Right? This is a profound implication of quantum mechanics, that even a particle in its lowest energy state has a non-zero energy. There's always a rest energy stored in the particle, and this is also found in experiments that they are never particles, no matter how much you cool a particle at its absolute zero point energy, there's still motion, there's still quantum mechanical thermal, well, not thermal motion, but it's really quantum mechanical rest energy and uncertainty in position, momentum, and so on. So there's still a blob in which the particle is delocalized. In other words, if you even cool it down, it never stops and becomes a point particle. Now we can construct states by action of this creation operators on the vacuum. This is really nice and will be really helpful. So acting with A dagger n times on the ground state gives us some state n. I call it n tilde for now. We know that the Hamilton operator acting on it, we know how the commutation relation works with the Hamilton and A, is just n, right? Because it's n times the A dagger action on the vacuum state. We can prove that it's a true statement. Plus 1/2 omega. right? So it's the nth state, and we said n can go from 0 to an arbitrary number, but the ground state has some energy with a factor 1/2 omega, and all the other states have corresponding energies that are 3/2, 5/2, and so on, increasing the energy levels. Now, the last thing that we need for this thing to be real state is that it's normalized. Yeah, we said that the norm has to be 1 for all states, and we can do it by taking the product of these two states with the n tilde, write down with explicitly a and a dagger construction here, and this is going to be part of the homework, so I will just sketch how it works here. In principle, you can always do a application of the commutation operators, and then you have to do it n times in this case, for example. When you take this annihilation operator and pull it through all the creation operators to the n operators here, then you go to the next step where you have n-1 operators here. And what happens if you pull through the annihilation operator all the way to the vacuum? It simply annihilates the vacuum, and that configuration is gone. But then you're left with n times the configuration where you have one a less on this side. So you've done this, and then you can show essentially that it's step by step, pulling through one after another, the a's through the daggers. You get n, then n-1 of these combinations, then n times n-1 times n-2, and so on, until you end up with the vacuum states annihilating vacuum states hitting each other, and this gives 1 because they are normalized, that this is by definition true, times factorial of n. So the product of these states is, or the norm of these states is the n factorial. So in order to have a state that is normalized to 1, we have to divide everything by square root of n factorial. And this is our final result for the states, the nth energy state of the quantum harmonic oscillator. It has the correct energy levels shown here, and this is called, in the quantistic language, it's called the spectrum of the Hamilton operator of the quantum mechanical harmonic oscillator. That's it. This is a very neat trick without doing any differential equations and solving of the Schrodinger equation. We showed algebraically how to find the spectrum of the Hamilton operator, the energy levels, and its energy states. Okay, again, before moving on to the field story of the quantization of the fields, let's do a brief recap of some mathematical facts that we will be using. One thing is going to be Fourier transforms. Yeah, French mathematician Fourier invented it, and we're going to be using it to go from position space to momentum space and vice versa. So if we have a function over momentum space, we can go to the position space by multiplying by the function by e to the I px, where this px corresponds to the correct norm of p and x on the space we are working on, and the space can be n-dimensional. So for practical purposes, we will have either 3-dimensional space or 4-dimensional space-time, and the norm will be either the Euclidean norm or the Minkowski norm here. And we will also take the definition that all the factors of 2 pi to the third power or 2 pi to the fourth power will be always living on the transformation from the position space to from momentum space to position space, right? And the inverse will have no 2 pi factors. It's just a definition, but it's easy. It's better to fix it and keep it forever. So here, to go from position space back to momentum space, we have to multiply by e to the minus I px, right? Here's the plus, here's a minus sign, and then we don't have no factors of 2 pi below the measure dx to the power n, again, being 3-dimensional space, Euclidean space, or 4-dimensional Minkowski space-time, and we get that takes us to the function in momentum space. Okay, now a reminder of the so-called delta function or delta distribution delta x is zero everywhere for all the x that are non-zero, and has also the property that it integrates to 1 when you integrate it over the space, the entire space. So it has essentially divergence at the origin and is zero everywhere. But its integral is finite and is 1. So you could think of it as the 1 in the function space. Good. If you have another function that you integrate over, f of x by the delta function x minus y over the entire space of x, for example, it takes just this function to the offset of the delta function, which is y. When y is 0, so you just have delta x, it takes you to to f of 0. Now, with the help of the Fourier transform, we have a useful representation of the delta function. For example, in position space, delta x, you could write it as dp on 2 pi of e to the I pi x. So it's the Fourier transform of 1. Yeah, the proof requires some steps and limit taking, and I will not show it here. So in general, the n-dimensional delta function can be written as this exponential, the integral over the complex e function, which is essentially the Fourier transform again of 1 in the n-dimensional space. And yeah, this will be quite helpful to evaluate many of the integrals we'll be using in quantum field theory, which we'll start with in the next lecture.